In the previous video, I have discussed about the three types of coordinate system, that is Cartesian coordinate system, cylindrical coordinate system and spherical coordinate system. Now, in this video, I will be giving the idea about the transforming of one coordinate system to another coordinate system. Here is the outline. First, I will show how the Cartesian to cylindrical transformation is done. Next is Cartesian to spherical, and lastly I will take some example for dealing the transformation. So let's start. With the Cartesian to cylindrical transformation, earlier I have told you that Cartesian coordinates are denoted by x, y and z point, whereas cylindrical coordinates are denoted by rho, phi and z coordinate. From the figure 1, you can see the x, y and z coordinate can be also represented by rho, phi and z. So firstly we will find the relation between variable x, y, z and variable rho, phi and z. X, y, z is the basically variable of Cartesian coordinate system and rho, phi, z is the variable in cylindrical coordinate system. So from figure 1 we can write x is equal to rho cos phi and y is equal to rho sin phi and z is equal to z. From this figure, rho is basically radius of cylinder and phi is the angle which is making from the x-axis. So if we break the component of rho along the x and y, we will find the y is equal to rho sin phi and along the x it will be rho cos phi, whereas in the z direction the height of cylinder is z. From this relation we can calculate the rho. Rho is equal to basically square root of x square plus y square. After squaring of these two component, that is x component and y component, then we will find the rho square is equal to x square plus y square, and simply we can write rho is equal to square root of x square plus y square. Whereas the phi in terms of x and y can be calculated using x and y. So x is equal to basically rho cos phi and y is equal to rho sin phi. After dividing y with x, we will find tan phi is equal to y by x. So phi is equal to can be written as tan inverse y by x. And z is basically height of the cylinder, which is same. Now we will find the relationship between unit vector ax, ay, az and the a rho, a phi, az. And this relation can be found with the help of figure 2a and 2b. From the figure 2a, you can see the a rho component is along the rho direction and a phi component along the phi direction and az component is along the z direction. If we break this figure into 2D plane, so a rho component will lie in xy plane. That's why I have taken here the xy plane as a figure 2a. In this, the a rho is making angle phi with the x-axis. So whereas the a phi will be in the direction of y, which is perpendicular to a rho. So if we break the component of a rho along the x direction, we find the a rho cos phi. A phi component is the perpendicular to a rho direction, and after reversing the direction of a phi, we will get minus of a phi. If we break the component of a phi along the x direction, so we get minus of sin phi a phi. So along the x, unit vector ax can be written as ax is equal to cos phi a rho minus sin phi a phi. From the figure 2b, cylindrical component of ay can be calculated. Similarly, in this case, a rho is making angle phi with the x-axis. So a rho will be break along the y-axis. This will provide the a rho sin phi. If we break the component of a phi along the y direction, we will find cos phi a phi. After solving this or sum of these two components, we will find ay is equal to sin phi a rho plus cos phi a phi. Whereas z unit vector will be same, because in the cylindrical coordinate system, the height of cylinder is same as in the case of Cartesian coordinate system. So by manipulation of these three equations, we can find the a rho is equal to cos phi ax plus sin phi ay, and a phi is equal to minus sin phi ax plus cos phi ay, and az is equal to az. Now we will have the relation between magnitude component of ax, ay and az with the a rho, a phi and az. Earlier we have this relation a rho, a phi, az unit vector with the unit vector ax, ay and az. So after the putting of this unit vector value of a rho, a phi, az in this equation, we will find this matrix relation. In this matrix relation, a rho, a phi, az, that is the magnitude in rho, phi and z direction, is equal to cos phi sin phi 0 minus sin phi cos phi 0, 0, 0 and 1 multiplied by ax, ay and az. That is the magnitude in x, y and z direction in the Cartesian coordinate system. Or we can find magnitude of ax, ay, az by inversing this matrix. So we will find cos phi minus sin phi 0, sin phi cos phi 0, 0, 0 and 1 multiplied by magnitude of a rho, a phi, az. Once we got the value of a rho, a phi, az magnitude, we put all these value in the vector a. We found this is the cylindrical coordinate system vector in terms of Cartesian coordinate system. So we can transform vector a that will be given in the Cartesian coordinate system, we can convert in the cylindrical coordinate system. Next is the conversion from Cartesian to spherical coordinate system. In this, we will find the relation between space variable xyz of Cartesian coordinate system with the space variable r theta phi of spherical coordinate system. From the figure 3, you can understand. Earlier we have break the component of rho along the x and y direction. The x direction component is basically rho cos phi and y direction component is rho sin phi. Now in the spherical coordinate system, two more parameters came into the picture, that is r and theta. R is basically radius and theta is the basically elevation angle or angle from the z axis. So now we will break the component of r along the z direction and normal to that. So along the z direction, r component will be basically r cos theta, which is equal to z, and normal component will be r sin theta. Normal component of r will give the projection onto the xy plane. So it will basically equal to rho. So rho is equal to r sin theta. Now we will calculate the relation between xyz and r theta phi. So look at figure 3. This is the triangle. This triangle is basically right angle triangle in which theta is the angle, r is the hypotenuse, z is the base. This rho is perpendicular. So in this case, you can calculate hypotenuse square is equal to base square plus perpendicular square. So r square can be written as rho square plus z square. Earlier we have calculated as rho is equal to square root of x square plus y square. So r can be written as r is equal to square root of rho square plus z square, whereas rho is equal to square root of x square plus y square. Ultimately we get r is equal to square root of x square plus y square plus z square. And we want to calculate the theta in terms of x, y, z. From this figure, you can say rho is equal to r sin theta and z is equal to r cos theta. After dividing these two, we will find r sin theta divided by r cos theta is equal to rho by z. So r will cancel out. This will give tan theta, and tan theta is equal to rho by z. And rho we have already calculated, that is the square root of x square plus y square. So theta will be tan inverse square root of x square plus y square divided by z. Earlier we have calculated phi and found phi is equal to tan inverse y by x. Simply dividing y component with the x component, we find the tan phi, and tan phi is equal to y by x. So phi is equal to tan inverse y by x. And the relation between r theta phi with x, y, z is also having some relation. In another term, x can be written as r sin theta cos phi, and rho is the projection of r. So rho is basically r sin theta. So x will be r sin theta cos phi. And y is equal to, we have calculated earlier, rho sin phi, and rho is the projection of r. So rho is equal to r sin theta. So we get y is equal to r sin theta sin phi. And z is the projection of r along the z-axis. So z is equal to r cos theta. Now to find the relation between magnitude component of r theta phi with magnitude component of ax, ay, az, the unit vector component are break and put into the standard relation. So after solving this breaking component, we will find the matrix relation, which is equal to sin theta cos phi, sin theta sin phi, cos theta cos phi, cos theta sin phi, minus sin theta minus sin phi cos phi, 0 multiplied by ax, ay, az, and this will be equal to a rho, a theta, and a phi. Or we can write ax, ay, az is equal to sin theta cos phi, cos theta cos phi, minus sin theta sin phi, cos theta sin phi, cos phi, cos theta minus sin theta, 0. This matrix is basically obtained from inversing the above matrix and multiplied by ar, a theta, and a phi. So finally, we can find vector A in terms of x, y, z after finding the value of ar, a theta, and a phi in terms of x, y, z. Let us take an example to understand this transformation. In this question, vector A is given by x plus y ax plus y minus z ay plus z az, and we want to convert this vector into the spherical coordinate system, whereas the given vector in Cartesian coordinate system. So let's solve it. From the given vector, we have ax is equal to x plus y, ay is equal to y minus z, and az is equal to z. And using the transformation relation, that is ar, a theta, a phi is equal to matrix sin theta cos phi, sin theta sin phi, cos theta cos phi, cos theta sin phi, minus sin theta minus sin phi cos phi, 0, and multiplied by ax, ay, and az. After the matrix multiplication, we will get ar is equal to ax sin theta cos phi plus ay sin theta sin phi plus az cos theta, and we know the value of ax, ay, and az. After putting the value of this component, we will get x plus y sin theta cos phi plus y minus z sin theta sin phi plus z cos theta, and then we know the relationship between x, y, z and r theta phi. That means relation between Cartesian coordinate system and the spherical coordinate system, in which x is equal to given as r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Then we will put the value of x, y, z in the ar. After putting this value, ar will comes to be r. Similarly, after multiplication of matrix and ax, ay, az, we will get a theta is equal to x plus y cos theta cos phi plus y minus z cos theta sin phi minus z sin theta, and a phi is equal to minus x plus y sin phi plus y minus z cos theta. And then we will put the value of x, y, z in a theta and a phi. After solving, we will get a theta is equal to 0 and a phi is equal to minus r sin theta. Finally, we will put the value of ar, a theta, and a phi in the standard equation, that is a is equal to ar unit vector ar plus a theta unit vector a theta plus a phi unit vector a phi. After solving this equation, we will get vector A is equal to r AR minus r sine theta A phi, which is basically in the spherical coordinate system. And this spherical coordinate system is obtained from the given vector in the Cartesian coordinate system. Thank you for watching this video.